Is everybody back?
Yeah.
Yes.
Yeah.
Okay. Well, let's continue. So where will we stop? Yes, we stopped talking about the variance as a good quantifier of how the property H is determined, right? So we have this collective, this many-body system, we have this collective observable, which is the usual thing which has a observable which has a typical classical analog, right? Or maybe last thing, yeah. So this is like really H, it has a spectrum, and now we know it's a pure state. So any variance in the spectrum is really comes from a quantum determinacy. So, like I don't know if you have like this is like Schrodinger cat state with two probabilities one half being here and there, right? So this is completely determined with two, but in general we can have like a state like this, right? And so it's not so easy to see. Just say, okay, how far away the states are, because it's indeterminate not just to be one or the other, but it's indeterminate in a range. But the variance, nevertheless, is still a good quantifier of how much this quantity can change. Yes, on the state, how much it is indeterminate in the quantum sense. Yeah, so this was to, again, try to repeat this argument of why the variance of a quantity like this, which has a classical analog, so a collective observable, is a good measure of how the state is microscopic, at least for a pure state. Yeah. And now that really comes the hard question is, what do we do with mixed states? So in other words, let's accept this now for pure states, that at least this is a way to quantify the microscopicity of the state. Right? So one way to say this then is so let's define this kind of microscopic quantumness. Yeah. We'll take it to be of state psi, and we will take it to be then the variance, for example, the variance of the state psi with respect to the Hamiltonian, and of course we have to kind of divide again by. So we'll divide by delta square and m, yeah, because then this will be just 1 for a product state. So it's just a matter of normalization, but this is a nice way to say it, right? It's like it's the same thing which we essentially did before.
I think you didn't turn the recording back on, just in case you want to record.
Oh yes, oh yeah, thanks.
I thought I told you.
Yeah, I'm actually recording. I have like another camera on another computer, which records on the camera, but I cannot make it work on the Mac for some reason because cables. Yeah, thank you. It's nice. Right, so let's just define this quantum like this. This is a macroscopic quantum of the state. It measures how much there is uncertainty on this property H. Yeah, but this is really, again, as we said, this really only works for pure state, because again, if you just draw this GZ state and well, okay, the distribution of the H, be it, I don't know, magnetization or how many cells are in life, is here or there, it can just be from the fact that we just don't know where it is. So the purity is essential for all this argument. So how to deal with the mixed state? Well, actually, one thing we can do is a bit similar to what we just did before. In other words, let's now look at the state. So we have a mixed state. So how to do it with a mixed state? What to do? What to do for a mixed state? What to do for a mixed state? Okay, let me also put a 4 here just for fun, because you probably guess why. It doesn't matter, right? So what to do with a mixed state? Yeah, a mixed state as before. Any mixed state of any mixed state of this bounded operator on this tensor product of small Hilbert spaces, right? We can decompose it. There are many ways to decompose it in pure states. So we can just consider any kind of possible decompositions. So mixed states, we can there's multiple ways to write. So like fix a decomposition, and we'll just write rho is equal to sum of some probability distribution over some pure states. Okay, pretty much as similar as we had before. And now, since now it's a mixture of pure states, to this thing now here on the right, we can attribute an average MQ, right? So with our definition of MQ now, since we have now the state as just a distribution of pure states, we can now give it an MQ, yes, by saying that okay, for this ensemble of states, we will just say okay, MQ is just pi MQ of the state psi I, yeah? And the macroscopic quantumness of the state psi I. This is what we attribute to this decomposition from our definition of mixed states. But as you can guess, and it's generally true, depending on which decomposition you fix here, so which decomposition you choose, so the decomposition is really just an ensemble of probabilities and the states, and the pure state which satisfies this equality, right? Depending on which decomposition you fix, this average might be different. So what do we take then? Well, we just take, actually, since we want to be kind of pessimistic, we want to be sure that the quantum effect is at least of this size, we'll just take the worst case, yeah? So then we can just do it as this, we can just define for each mixed state as well. We just say, okay, let's just associate this number MQ for the mixed state as just being the minimal possible average over all possible decompositions, right? Needless to say, that of course, this is a decomposition of the state. So this minimum is only constrained, and this is really decomposition for all, right? Actually, this is called the convex roof construction. I mean, I don't know if you've covered this before, but in quantum information, kind of happens quite often when you have something nice for mixed states, for pure states, and then you want to lift it to mixed states, you can always formally write this equation, right? But of course, so for the moment, if you look at it and say, well, okay, but this is just storable, right? Okay, we can write it certainly, but how do you compute the thing? You have to consider an infinite number of possible decompositions and compute the thing, the variance, the average variance for all of them. Sounds like it's crazy, but in fact it's not, because this thing is actually equal to the quantum efficient information, it turns out, of the state rho. Yes, and this is a bit lengthy to prove, but it's nice to prove. So I think we'll just, last hour we did some big claims. Now we'll just spend some time proving the statement really technically. Okay, so my claim now is that we are going to prove a statement. The statement is that the following is that really, okay, actually, this is true without this division, right? So, okay, so let me just write the statement. So the statement is as follows: is that so you agree with this intuition, right? Here we're kind of being pessimistic. We're just considering for the worst case decomposition, which gives the minimal quantum effect. Nevertheless, this is certainly there whenever the way you prepare the state, whenever the way you want to look at the state as an ensemble of pure states, right? So this convex roof is kind of makes sense. Now let me just formally write the statement. So the statement is that if the following is just a minimum. So for a state rho, the minimum over all decompositions pi, right? So the probability and the pure states of preset is a quantity 4 variance. So wait a second. So sum of pi, right? 4 times this time of the variance of the ci, right? The variance for the fixed operator h, such that, of course, rho is equal to, so such that this is indeed a decomposition, pi of psi I. This thing is equal to the quantum efficient information of the state rho with respect to the thing. That's kind of the claim. And then, since this is true, and then if you accept all the argumentation before about why the variance is a good measure of this uncertainty for a pure state, then automatically the Fisher information becomes a good measure of this macroscopic effect, right? For a mixed state, yeah. But it's actually not easy to prove, so. So let's do it now, right? Не, тут занимай, подожди. Видишь хорошо?
Ну, дела, Софья.
Нет.
Ну, где он? Я так думаю, где-то.
All right. So let's now we spend some time proving, because it's actually not so trivial, but it's a nice exercise as well. So what we want to prove is, so right, we have a rho and we have all the decompositions. Sum of pi psi I, right? Yes, we want to kind of find the average variance for all the decomposition and then prove that indeed this is equal to the Fisher information of the state. Okay. To do this, we actually will pass through the fidelity, so the fidelity definition of the Fisher information. So remember that this thing, fish information of the state row B, right? This is just 8 times the limit of the fidelity between the state row at 0, right, and row at B. So 1 minus the thing divided by dB squared. If I remember correctly, there is 8. Then B goes to 0. Then yes. So instead, let's just look on this quantity first, right? Because then we take a limit at the end. So in other words, we can look on the fidelity, an average fidelity of all the contradictions, and this is a nice thing, or yeah, whatever. So let's now, and the other thing is that, so let's first point is that let's look on the fidelity, right? So look at the fidelity of rho and rho B. Yes. You remember we can use the Ullmann's theorem, right? This is the object we're going to look at. What did the Ullmann theorem tell us is that if we have the state rho, so we have a system here, system. This is a big critical many-by system, but now it's not important for this. It's many-by. Then we can just add an auxiliary system, like we had Alice and Bob, and then we define a purification here. So for a state rho of this system, we will have a purification, which is a pure state phi. Yes. Such that, so purification is a state on the two systems, the system, original system plus the Chile here, such that rho is equal to trace over, let's call this A and we call this B. When we trace out B, phi, yes, we recover thing. And indeed, if you remember, the Ullmann theorem told us that the fidelity is actually the maximal. The fidelity is the maximal fidelity between purifications, all right? So the fidelity between two quantum states is the maximal fidelity between psi, purification of rho 0, and so phi and phi b, right? Where phi 0 and phi b are both purifications of these two states. Yes? So this gives us rho 0 when we trace, and this gives us rho b when we trace. Okay. So now, what do we get from this? Well, actually, first thing we get is, because these are pure states now, fidelity is just simply rho 0, psi b, so it's not rho, sorry, phi 0, phi b, just overlap of the vectors. Yes? Good? So that's what we start with. Right, so now we have a chain of arguments. We have the Fisher information of the things is the limit of 1 minus this thing. Now that means that because it's so the fidelity is the maximal over things, and the Fisher information is the minimal Fisher information over the purifications of these two states. And then we take the limit. But let's just work with the thing. We know how to go back to the Fisher. So consider now our state rho, right? Rho b. This is just equal to, with our encoding bh, our Hamiltonian, rho 0 bh. Yes, and of course we only care about first order expansion. And now, if you remember, how did it work? We also had this. So now, in other words, now if you have a purification psi 0, right, a purification of rho. So I just remind you again, it means that if you trace out the auxiliary system, we recover our state rho 0. Then what we get is that the purification of psi b of rho b. This is just identity. So we act with our unitary here. So in other words, this psi b is equal to E minus I BH tensor identity. So tensor identity acting on psi 0, right? Why identity? Because we introduced this auxiliary system, right? And the real system is here, right? So the evolution acts on the first one, and this one is just the auxiliary system. Yes. Another thing is that we want to have a maximization overall. So now back. What we want is the overlap of these two things. So what we care about really is maximum between these purifications psi 0 and psi b of the quantity psi 0. It's not psi, sorry. Of their overlap. All right. Now we need also a way to kind of go through all possible purifications. And if you remember again from the Ullmann theorem, that again, it was not important actually. We can fix first of them. This is just a corollary we had. If we fix phi 0, for example, to do some purification, we can only run the minimization through the other one. So because kind of purifications are related by unitary here, it actually doesn't matter where which unitary acts here and there. It's only the relation between this unit, which is important. Do you remember this roughly?
Yes.
Yes? Okay. So in other words, what we do is we precisely fix this phi 0, right? And now the maximum, so this thing, we say this is the same as maximum for a fixed phi 0, it's maximum over phi b, right? Over the overlap. Phi 0, phi b. All right. And finally, we have this story that changing the purification, running through all purifications, is the same as just applying a unitary transformation on the Archila system. Yes. So in other words, we can say that now all purifications. We've seen it, but I'm not sure you remember. So all purifications phi b, right? They are equal to they can be parameterized by just having identity on Alice and some unitary transformation acting on the system of phi b. Yes. Okay. So now we can just plug this all together. So then we have simply max of this guy is the same as this thing is equal to max over the possible unitary transformations acting on the ancillary system of phi 0 and phi b. Sorry, now here we have this identity tensor, any kind of unitary transformation on phi b. All right. So far so good. So and this is really the object we want to work with now. So so what we want to find in this story, we want to find max over all possible unitaries acting on phi 0. This general unitary acting on Bob. And remember, we had this E minus EBH, then the general unitary acting on phi 0. Because this is how we get in general phi b. All right. And the trick now is just to do this order by order. Because at the end, we don't care about, so we know that the max, we take it on the around b equals 0. Since we will get the Fisher information. And then, is it clear? So this is, we just really use the fact that the encoding is unitary here, and we use this, all the notions we've seen related to the Ullmann theorem. So all purifications are given by this unitary acting on the ancillary system. Yeah, so if you just go back to the notes, otherwise, if you don't remember this. So now we can do it order by order. Actually, any unitary as well around the. Okay, let's do it. So the fact is that this, you see, so we have now a curve of states. So we have this kind of psi 0 state, right? And then we have a curve of state psi b with the unitary. So the point here is that this unitary can also depend on b. It's kind of a virtual unitary. It's kind of a gauge freedom, right? It doesn't measure anything physical. This is just a different parameterization in unitary. Nevertheless, it can still depend on b, and actually it will depend on b to maximize it. So depending on which b you take here, this unitary will be different. The unitary which maximizes will be different. So actually, we will put here a formal dependence on b. And well, since we have a formal dependence on b, we can also expand it in order. So first, let's expand this guy in order. So obviously, we just have e minus bh. Well, this is identity minus ibh, and then I guess plus minus 1. Right, square, check, minus 1/2 b square h square. All right. Okay. Now, what can we say about ub? Can we also expand it in orders of b? So this is plus orders of b cube, and orders of b cube, we don't care about them because at the end we want the Fisher information. So anyway, take the limit b going to 0 and divide by b squared. So these orders will be gone. Well, if you look at the zeroth order, it's clear that at the zeroth order we want the maximal to be 1. right? This is a possible maximum. But since here we have identity, it means that UB, right? So, okay, let's write this. U0 minus I, taking minus or plus, minus I. Now we have some operator here which we call G, B, right? G is just the first order expansion, or let's call it U1 of B, plus minus 1/2 B squared, and then we have something like U2, yeah, U2. No need a square, or do we need a square? Yeah, let's keep it as. Yeah, so maximization, meaning now maximization over U means that we maximize independently over all these first order guys. First zero order, first order, second order. So we can straightforwardly maximize over the zero because we see that to the leading order we have here, right? So this expression here, psi zero, UB tensor E minus EBH tensor UB of phi zero. Like to the leading order is this psi zero, right? This guy gives identity, nothing. Identity tensor U0 psi 0, right? And we have to maximize to the leading order. So to the leading order, U0 is equal to identity. That's what maximizes it. All right? Good. So already we can say that this guy we can fix it. This is just identity. Now, the second one I will call it G, simply because I want to put G. And now let's look. Yeah, let's just redo it order by order as we. So second order, so first order, psi 0, phi 0, sorry. Then we have identity minus. No, but what am I doing? This is just do everything all together, no? So, for this expansion, psi 0, 1 minus I VH minus 1/2 B squared H squared. Then the product 1 minus IG B minus 1/2 B squared U2. Okay. So 0 overrides. So now I can forget it, guys, because we don't need them anymore. And we can just collect the orders. So we get psi 0. Well, 1, which we've seen already. Then the first order is minus IB, and here we get H plus G. So formally we have to write H tensor identity because H acts on Alice, on the real system, and G acts on, so plus identity tensor H. All right, this is the first order. Finally, the second order is plus, no, minus 1/2. And now we get many things here in the second order. So we get minus 1/2. First, this one square. So this one squared, this will be B squared. B squared, or B squared is actually everywhere. B squared, we get 1/2 as well. B squared, H squared, right? Tensor identity. Then we get this guy. Minus 1/2 B squared H. Oh, that's many terms. Tensor identity. The next one is the cross term here, right? Which gives us plus, no, minus. Plus I, J, plus J squared, B squared. B squared is gone. Identity tensor this guy, okay. Yeah, just minus again, minus 1/2 B squared U2. And finally, the cross term is a minus H tensor G. Okay. So what can we conclude from there? Let me remind how did I do this proof? So is it right? So this is fine, right? Now that's one I have to combine them in a nicer form. Let's just see how. So actually what I have written here is that this guy is equal to, let's just check it now. So the first order is fine, I will just keep it like this. And the second order I have written here that this is b squared over 2 times h tensor 1 plus 1 tensor g squared. Is it true? With 1/2. So we get, you need to get this cross term. So -1, no wait, no, something in front here. Well, let's just do it again, no? Sorry, it's a bit, I don't know. The first order is fine, we keep it, okay? Now we do the second order. Again. Second order. Oh, come on, I just asked them to calm down a bit now. Do you hear my daughter?
A little bit.
Well, not easy always. Always easy. Good. Yeah, and it's also be concentrating. So second order, right? What did we say? This guy squared. It's so first order was b minus ib h tensor identity plus identity tensor g. Okay, and the second order now we get minus. So we get minus b square h square tensor identity from this term times itself. Okay. All right. Then we have this term times identity. So it's again minus 1/2 b square h. Oh wait, no, but what are we doing? Of course, no, there is, sorry, no. Do you see the problem? I'm sorry. there is no such term here. This guy is not squared, right? So there's basically just 3 terms in the second order. Yeah, so there's this term, the cross one, right, which gives a second order, this guy times identity, and this one. Yes? I know, I was squaring the bracket, so the parentheses, so we know what happened. So we get in the second order, we get minus 1/2 b square h square, right? This I times I, it's a minus b square h tensor g. All right. Minus, finally, 1/2 b square u2 identity. So this is tensor identity, and this is identity tensor this guy. This is what we need. Okay. Now, in fact, this should be h square, the u2. So this I don't remember how I did it. Let's just assume it, okay? Well, you get, so here actually we can prove that this is g squared, right? I don't remember the details, unfortunately now. But you see, so this is like the same expansion as normal Hamiltonian expansion of the integer, right? So So this is written. I think it's written in the notes properly. Okay, so this we get G. Do you accept such a step if you just do it like this? Fine.
Yeah, it's fine.
I mean, does it make sense to lose time and find where it comes from? Yes. So here we get. Oh my god. Yeah. So coming back, we get psi 0. Then this u times this u e minus bh and the u b, right? This was the first order, we get 1, then we get minus I, remember psi 0, h tensor identity plus identity tensor g psi 0, and this guy now is clear now that it's the square, right? Minus 1/2 b squared phi times b h tensor identity plus identity tensor g squared phi. Yes, this is what we want. This is what we want to minimize. Now, minimizing over u now, right, is the same thing as minimizing over g here. So all this unitary freedom we had for the from Ullmann's theorem, this just becomes a maximization. So we want to maximize this thing over g now, right? G is our basically g is it plays a role as Hamiltonian in this gauge unitary thing. Yes, and yeah, and now so this is basically the final step, and then it becomes a classical problem. Because what we want to do now is that we have this, we have this, so we have the maximization of g over the story. But let's just take this g. G is an operator, a Gaussian operator, which acts on the auxiliary system, and we'll just write it in the basis where gk, kk. We just write everything in its eigenbasis, right? So once we write it in the eigenbasis, you see what we have. So we fix this basis for the g operator, and now we can take this. We can take this phi 0. Phi 0 is our purification, but it's just a pure state, so we can also decompose it in any basis we want. So in particular, we'll take phi 0, and we will express it in the basis for Bob. We'll express it in this k basis. So we take sum of k. Now we do the sum psi k, right, times k with some probability pk squared. Yeah. But this is what I say here, that any pure state of two systems, we can just express it in any basis for Bob, and then we get some states here that are not necessarily orthogonal, only k are orthogonal in general. But still, if you trace k here, right? So you see, if you take the state, we trace k, it means that from tracing out k, tracing Bob now, we get phi 0. Phi 0 is equal to, well, k orthogonal, so this is sum of pk. Wow. Right? So actually, that's precisely what we see, the thing emerging here, because from a purification, we actually come, you see, by fixing this basis of J, we come to a decomposition of the state in an ensemble of pure states, right? Here. And this is just what we're going to plug in now in this formula. So plugging this in this formula, we get that for this story, we get max over possible basis. So we get this phi 0 phi b thing. Yes. This is equal to 1 minus I. And yes, let me just maybe erase this thing. So you see when we apply in this J on phi 0, identity tensor J, we really get GK, right? Because in this basis they are orthogonal, times PK times psi K. All right? Yes. So writing it down, what we get is our overlap phi 0 phi b is equal to 1 minus I sum over pk of expressing by the values of psi k h psi k minus simply gk, right, times pk. This is for the first order, all right. And for the second order, I'll like change the color, maybe that it look super visible. And for the second order, we get minus 1/2. Well, I just copy it now, but you get the idea, right? So, like, let's. So this was what, minus 1/2 phi 0. So now let's just write it down, right? So 1/2 sum of k psi k k square root pk, and here we get h tensor identity plus identity tensor sum of gk k k square times sum of l. There's another index here, I, right? Psi l, l and pl. Yes, this is what we want. And clearly, what we get here is this thing is now 1/2 sum of k. You see k on h. So k and k, this is diagonal. So basically, we only get k has to be equal to I and has to be equal to L, right? Because we're working, everything is expressed in the same basis. So we get here sum of pk, and we get psi k, right? And we get just the operator here for a, h tensor 1, and plus gk, here it's a number. Because on the k state, it just gives us this number gk squared. Psi k. Okay, good. So now we get all the orders. And the k is gone, so there is no identity anymore because we traced out the k already. Right? It's really just simple. Oof, good. So combining the two, we get that. We get that the sum is so this phi 0 phi b, right? This is equal to the sum of k of pk of 1, the first term, minus I psi k h minus gk psi k. I just write it down. Minus 1/2 b squared. Yeah, there's a b here. Sorry. 1/2 b squared psi k h minus gk psi k and then square here. Yes, and this all absolute value. All right. Now the absolute value. What happened with absolute value? Of course, you can see that gk. So gk is a real number. Yeah. H is an Hermitian operator. So this part is imaginary, and the rest is this is imaginary, and this one is real. So when it takes absolute value, we'll just take the square root of the sum. Yeah, so we get sum of pk 1 minus 1/2 b squared psi k h minus gk squared psi k. This is the real part, right? We get squared plus the imaginary part squared. The imaginary part in this one. The imaginary part gives us sum of pk psi k h minus jk psi k squared. And all this square root. This is because we have an absolute value, right? Yep. So far, so good?
Yep.
Yes, and now, so what we want now is, in fact, simply the minimum, right? So all this minimization over gk is actually, we want the max, so we wanted the maximum fidelity. So we want the maximum over the possible numbers gk, because gk are just properties of the Hamiltonian h, which was completely arbitrary, right? We had precise maximization over it. And of course, also of the purification starter, so we can plug it back. So this pi and the psi I, yeah? Yes, so now how to do it? Well, this I think it was kind of a simple story. Maybe that's just, I won't be able to reproduce it now, that's the problem. So it's almost done. So, the idea here is that this is really maximized when, so now we have to show basically that this thing is maximized when gk is equal to psi, the expected value of hk, yes? Or in other words, where this term here is always 0. Now, is it trivial to show or not? 5 minutes left. Yes. So, okay. Actually, now I remember how I did it. So, one way to do it is simply just to derive with respect to all gk. Yeah? So now we have a quantity which depends on all these gk's. Yes. So something we can do is we just, so we have an expression on this, all these parameters. So this is the fidelity of gk vector and purification. So what we do is we just take our quantity, we derive with respect to the fidelity. Yes, so the gk can be arbitrary from minus infinity to infinity. So the only way it hits a minimum or an external value, because there is no boundary, or otherwise this quantity is infinite, right? But this is clearly not the case, in fact. But the only way to have minimum is the derivative with respect to all the gk's are 0, right? So what we just do is we derive with respect to gk's and we find the local minimums. And since we have gk's are completely undefined over all the real line, these are also the external values for our thing. We just have to check that the second derivative is also kind of that it's a maximum, right? So how to do it? Well, if you derive, so we have here, well, we have 3 minutes. I think it does make sense. So just believe me that, and you can really know that if you derive it, you see here, I just get, well, this gk here, since it's a square, well, first thing, we can forget the square root, right? If you maximize the thing, we also maximize the square root. So we'll just remove it for the derivation, so we can derive the square of this function. And then, well, we just have some equation here, and it turns out that precisely to solve this equation, we get gk is equal to psi k h. Psi k. This is actually the condition with which we get minimus. Good? Do you believe me on this? So minimize this quantity. Minimize this quantity, we actually get this expression now. And now finally, we get to the point because once we plug this in, we actually get precisely what we want. Because here we get 0, or is it true? Here we should get 0. Yeah, no, so sorry, here we get 0, right? Because it's h. So here we precisely get psi k of h minus gk, which is equal. So this term disappears. Yes. Now this terms, if you open the bracket, what we get is h minus gkh 2 times plus gk squared. Okay. H squared. And now because this is all psi k. So you see that this guy gives us psi k h squared minus 2 times psi k h psi k gk, but this is guys are equal, so this is just the square, plus psi k h, so plus gk square, which is this guy square, right? So this just removes 1 here. Yes, so we get, so this expression here is this one, finally. And okay, admittedly we didn't do the proof properly, but you've seen the big lines, no? That's now 1 minus 1/2 b squared, right? And sum over psi k. So psi of some psi k h squared, right? minus psi k h squared. All right, and you see precisely what we get. So we get that we get the variance here. So this is the maximum. Remember, we had the maximum over all possible purifications. So this is the maximum over all these purifications pk psi k of the quantity 1 minus 1/2 v squared, and the sum of, well, there's a pk here, obviously, which comes from here. Sum of pk of the variance of our state psi k of the Hamiltonian h. Okay. Now the only thing which remains to be done is just to put it back in the Fisher formula. This will remove this minus 1, and then we'll divide by v squared. And there is a factor 1/2 missing somehow. Disappeared, but believe me, then at the end we precisely get the Fisher information, which we started with. So the Fisher information of rho for v, or for how we wrote it today, of rho with respect to the operator h is equal to precisely the minimum. The maximum becomes the minimum because it's 1 minus the fidelity, right, in the Fisher information. The minimum pk and psi k, new decomposition of the average variance of our decomposition. Okay, good. Oof. That was difficult. Somehow else I was a bit deconcentrated with dollars crying there. But yeah, that's the message we get, right? So this gives another interpretation to the Fisher information. Okay. And it's particularly interesting in light of what we just discussed before. So if you say the variance of this collective observables is a good measure of how the state is microscopic, then the Fisher information is kind of how to extend this intuition to mixed states, right? Because the Fisher information is precisely the worst case average variance you can get with a mixed state, decomposing it in pure states. So it's actually, formally we'll say, the Fisher information is actually the convex roof of the variance, defined for pure states. Yes, so that's the thing. And also, what now it's important, and we come back to this a bit, it's interesting to look at this from the perspective of fragility of JZ states, right? You remember we discussed last week that JZ states are kind of super fragile. And it seems to be a general property of states with high Fisher that having a high Fisher information is difficult to preserve. Whenever you have some kind of generic noise, it quickly falls down to an end scaling. So if you think of it as this little bit microscopic quantum effect perspective, it tells you that, well, yes, actually this kind of large microscopic features, they're not easy to maintain. So whenever there is some tiny noise and n grows, they will be very difficult to observe, right? So this is also comes to, at least, this gives you some kind of emergent quantum to classical transition, right? Just simply because it's not something fundamental, but it just comes from interaction with environments, which makes it then look as there is nothing microscopic quantum. But we will come back to this fragility again, even from a more general perspective. Nice. Do you have questions on this? Or admittedly, the proof was not very easy to follow.
Yeah, just a question on how we can interpret this last formula, meaning that the Fisher information for a mixed state is that for which that quantity with the variance is minimum for a given purification of a state, right? Given the whole procedure. Yeah. Mm-hmm. Yeah. Is that the purification? Mm-hmm.
Also, a state, it corresponds to multiple purifications, right? So you can take one. I don't know, there are like infinitely many possible purifications. I don't know, let's say like this 5. Yes? Right? So if for a state there are many decompositions like this, actually as many as purifications as we just used. And each of these gives you kind of an average variance. Yes. And the interpretation of the formula that actually to the Fisher, so you can relate the Fisher information of the state, you can compute it by finding the one for which this quantity is minimum, right? And then it's equal to the average. Yes. So one way to compute the Fisher information would be to kind of consider all possible decompositions of the mixed state and pure states, compute the average variance. Well, because I forgot the 4 here. And then once you find the minimal, this is equal to the Fisher information. We just actually proved it. But of course, typically you do it the other way around. Typically, this is much easier to compute because they have other means of computing it, right? Solve the SLD or whatever. So it's actually more like you know this quantity, and this gives you some interesting interpretation of what your state is, right? So your state is, so that's how I would see. Does it answer the question?
Yeah. Thank you very much. Makes sense now.
Yeah. Another thing I wanted to discuss today is how to witness this thing, this fish information in practice. Like given the state, right? How do you measure this fish information? But then the thing was just delegated to the exercises because it's actually nice exercise. It's not technically created like the proof. I mean, the proof is not so bad. I just too long to follow. Yeah. So that's it for today. If you don't have more questions.